Okay, the purpose of this tutorial is to refine the initial HEC-RAS simulation or model that we ran last time that we noted one small potential problem with. We want to refine that and then rerun the simulation and analyze and compare the results. So just to be very clear on what the issue was, if we bring up, I've got the solution here that we ended with last time. If we bring up our detailed output, if we go to our most downstream section, river station 0, and then we move upstream. Remember, depth was critical here. We had these 3 warnings, and the results of these warnings all said this may indicate the need for additional cross sections, and that's because between 0 and 100 meters, we expect sharp water surface curvature that is not captured by our cross-section spacing of 100 meters. So we'd like to refine that. Okay, so I'm going to exit this. I would like to keep this water surface profile to compare against my new one. So what I'm going to do is bring up the summary table, and I'm going to show you how to put this into Excel. So what you can do here is copy the data to clipboard, and I use the data in headings. And then I'm going to bring up Excel. And in this file, I've created one new tab for geometry 1, and I'm going to go ahead and paste my data. So I can do Control V, or I can do the paste option there. Okay, just note, whenever you paste this, if you have interpolated cross sections, these asterisks show up, which is a little bit problematic. So I'm just going to replace them with the same numbers without the asterisks. This is where you have constant spacing is very nice because I can just type in the first 2 numbers and pull down, and there we've got an answer. And what I've plotted here, I've created this plot that's been populated here, is the water surface elevation over the minimum channel elevation or channel bottom. So this is the same as the profile plot in HEC-RAS. I've just done it so we can see it here. Again, there's your river station, there's your water surface elevation, there's your river station versus your minimum channel elevation. And we can see clearly in this plot, this area where we're not capturing the curvature very well. Another plot that you might want to create, I've done here, is flow depth versus the station or distance along channel. And notice it's not populated. That's because if you look at these quantities, flow depth is not one of them. So I'm just going to create one. The nice thing about having the data in Excel is we can do some manipulations. So what is the flow depth? It's the distance from the channel bottom here to the water surface elevation. So this gives you an idea of how we can find it. We can simply take the water surface elevation and subtract our channel bottom. And notice we get normal depth here, 1.75. And then scroll through the table, and then it goes to critical depth, 1.03. And now it's populated. And again, you see here, we've got 2 points here defining that curvature and a straight line fit between them. We'd like to do a better job of capturing that. Okay, so how are we going to do that? Let's go ahead and save this. We want to use this for comparison later. I'm going to go back to our initial HEC-RAS model. So our geometry needs to be refined. So I'm going to open up the geometric editor. And I want to refine in this region. So I'm going to get rid of all of these interpolated cross sections. And this can be done quite quickly with that cross-section interpolation tool. So we go back to where we were before, interpolating between 2 cross sections. And we're going to use this option, delete existing interpolated cross sections. We do that, and now we're just back to our original 2 that we did in the first geometric tutorial. And close, and see we're left here. So what I'd like to do now is insert a cross section here, say at 100 meters, so that I can have nice dense cross-section spacing here where I need it, but not somewhat dense out here where I don't need it, where the water surface is changing more slowly. This is using our computational resources more efficiently, basically. Okay, so we'll go to our cross-section editor tool, and notice it actually keeps the water surface from our solution. Don't let that distract you. And again, so we've got just our upstream boundary and then our downstream boundary. So what I would like to do is take advantage of some of those copy tools, and I'd like to copy this cross-section. So I'm going to go to Options, copy the current cross-section, and I'd like to place it at a new river station. I'm going to use 100. Okay. And remember, once we create this river station 100, it's no longer the downstream boundary, so I'm going to change the description. I need to apply the downstream reach length. So if we're at river station 100, the next downstream cross-section is at 0. So our distance from 100 to 0 is 100. This tells HECRAS where to put cross-section in the channel. Manning's End hasn't changed. Our bank stations haven't changed. So we can apply the data. But we might remember again, we need to change the elevation. And we have a bed slope of 0.001. And so the increase in elevation over 100 meters of a slope of 0.001 is an increase of 0.1. So I could simply type 0.1 next to all of these, or I can take advantage of that adjust elevations tool. This is really saves you a lot of time when you get comfortable with these tools. I'm going to increase it by a value of positive 0.001 and click OK. And there you go. Apply the data. And I think we're in pretty good shape. Let's take a quick look at the profile to make sure that it looks nice. And it does. Notice it kept our solution. Don't let that bother you. We're just looking at the bed slope. And it looks pretty good. Although notice it got off here. And the reason for that is we need to go back to our upstream boundary. And it's no longer, the downstream reach length is no longer 1400 because we're now moving downstream from 1400 to a new cross section we've placed at 100. So this distance is now 1400, and this is a key change that we need to make. And so we've changed all of those downstream reach lengths to 1300. Everything else stays the same. The elevation stays the same. We figured that out the first time we set up the geometry, and it's correct. So we go there. And so now we have our downstream boundary at 0, our river station at 100, and our river station at 1400. Okay, and now if we plot the profile, everything should look good. And it does. Looks very nice. And we can exit here. All right, so we've done that. What I would recommend, and notice here, now we're seeing the layout as we would expect to see. A cross-section at 0, a cross-section at 100, and a cross-section at 1400. Since we've changed the geometry, let's save this as a new geometry file. Let's call it geometry, since we've modified it, and click OK. The next step is to go back to the interpolation tool. And again, we can interpolate dense cross sections here and not so dense here where we don't need the dense spacing. So again, tools, cross section interpolation tool, which I hope you're getting the sense that this is an extremely useful tool. We use it all the time, and go between two cross sections. And we can do this. This is the one. So this is the upper river station of 1400. Let's go to 100. And so we've got 100 and 0, a distance of 100. We can again do a constant spacing interpolation. I'm going to try 10 meters. I think this will work well. And I'm going to interpolate new cross sections. And there you see them. Looks good. I'm going to keep those. Now I'm going to go to the region where we're less concerned about capturing. We don't have large curvature to capture. So go between 1400 and 100. And I could do a constant distance of 10. Let's see what that looks like. So it's 129 cross sections. That's pretty dense. That's overkill. We don't need that. So I'm going to delete those. And I'm going to use a constant spacing of 100. So again, constant distance of 100. And interpolate new cross sections. And it looks good. So I'm going to close now. And now we see a very dense cross-section spacing here from 0 to 100, and then from 100 to 1400, our original spacing, which seemed to work well. Okay, and let's save our geometry as geometry 2, and we're done. Okay, now this is where the kind of modular features of HECRAS are really nice. Our flow quantities haven't changed, so we don't need to change anything in our steady flow data. We have the same boundary condition, critical depth at the downstream end, and we have our same flow. So we don't need to change anything here. We can simply set up a new plan. So we go to the running man to run our simulation, and we can start a new plan. And we can call this a plan. And our short identifier will be P2. And so now we have two geometry files to select from. Again, we want to use our new one. Flow, we've only got one flow file. That's fine. We'll keep that. Subcritical, we still believe it'll be subcritical, and we can go to the compute stage. So let's compute. Okay, this should go fairly quickly, and it does. No warnings or red text here. We're good to go. We've now got our new solution. So we can close this. Let's save our plan, and we can exit. Oops. Let's hit something else. Exit. Now we can start to look at our solution. So again, the one I like to look at first is the profile. So let's look at a profile. And you can see here with our dense cross-section spacing, we've captured that curvature much better. It's no longer that clunky straight line. Okay, and this looks pretty nice. Again, on your own time, I would play around with some of the options, figure out how you can make these plots look nice, better. There might be things you want to see that are not shown here. I think the defaults are generally pretty good to troubleshoot. And then if I want to plot other things, I'll oftentimes go to Excel, as we saw earlier. Okay, we can look at the cross sections here, and again, we might go to our downstream boundary, and note again we have critical depth. It calculates critical depth at 10 meters, but it sees it's subcritical, and flow depth increases, so it doesn't calculate critical depth anymore. And we could click through all of these to see how it's changing, but you can do that on your own time if you want to. And again, look at the options to see how to plot different things. Okay. The next one that will be quite interesting for us to look at is the 3D plot. Let's see what that looks like. Wow, that's great. You see our cross sections here, and you can really see the water surface and how we've better captured that curvature. Looks really nice. And you can copy the plot to the clipboard if you want to insert this into a report or something for your client. It looks nice though. And we can go again to our detailed tables to look at the different cross sections to see if we got rid of those warnings. So we want to go to 0, and again we've got critical depth. As you get comfortable clicking through these, you'll start to see very quickly which quantities you need to look at a lot and be able to find them faster. And if we go to 10, the next one upstream, you can see the velocity had changed by a large amount, more than half a foot. So this may indicate the need for more cross sections. We could go and refine further between 0 and 10, but I know from experience that this will be fine. And we'll notice if we go to 20, there's no more warnings, and we can click through and see how the different flow properties change if we wanted to. And we can copy this table into Excel if we needed some of this data to plot or do some computations with. So I'm going to exit. Last thing I'm going to do is look at the summary table, and I want to take this into Excel and actually plot the flow depth and water surface elevation similar to what I did for geometry 1. So I'm going to go here and copy clip. Oh, you know what? Before I copy there, I'm going to go to Excel, and I'm going to copy this sheet, the geometry 1, and I'm going to move it to the end. And I'm now going to call this, instead of geometry 1, I'll call it geometry 2. I'm going to take all of the data and delete it. Okay, because I would now like to go to this table and copy and now bring up Excel, and now I would like to paste this data in. Okay, and again, Excel does not like the asterisks, so I'm going to go 1400. Now remember, our spacing is not uniform here, so I'm going to drag to 100. And then here, 90, 80, etc. I'm going to do this. Now notice it doesn't give me the whole profile here because, why? I need to select my data. I know it does not go to the end, so we need to go to cell 26, or let me show you this visually so you can see what I'm doing here. My X series values are now here. My Y series values are now, this is the, are now here. Oh, that's obviously the wrong data set, my bad. They are here, water surface elevation, great. And so that extends to cell, or to row 26, so I can do the channel elevation a little bit faster fashion. I'm just going to change the 1726, but I'm doing the same thing graphically, or quickly that I did graphically before. Okay. I'm not crazy about the markers when it gets this dense. It gets a little bit harder to see, but basically you can make out here the water surface elevation is, we've captured that curvature much better. Let's go ahead and take those markers off. And there you go. It looks a little, Excel kind of has these funky kinks in there, but that's okay. It's not in your solution. That's just in Excel. And similarly, we can plot our flow depth. So actually, I can go back to the previous sheet. What I'm going to do is just copy that and there, and I can scroll down to plot my flow depth. And again, it doesn't capture the whole thing because I need to update my data. I'm going through this kind of quickly because I'm assuming most of you are experts in Excel, or at least better than I am at it. Okay, let's have a look at how our flow depth, and there we see how our flow depth changes, and we see that, let's get rid of the marker. Very nice. Very nice M2 water surface profile. And what we can do now, once we have it in Excel, we can do some fun things. For instance, we could compare this clunky, segmented water surface profile with our improved solution. So I can go here simply and select data. Let's add something. Let's call this geometry 1. And we can go to this table and we can import this, insert this data here for the water surface elevation. And then we might want to rename this one. So let's edit it. Let's call this geometry 2. Or even geometry. There we go. The reason to do that is so that it turns up in our legend. Okay, and let's select. Oops. Let's modify this data point because, or sorry, not this data point. This line. Make it a different color so that we can compare them. So let's make it a really nice, really contrasting color, like say red. How about this red? Okay. And what else might I do? I might change the order like that, so you can really see geometry 2 and geometry 1. And if you really, another thing we might do is we might change the scale here. Let's just look at, say, the first 200 meters. You can see clearly how we're doing a better job capturing that curvature with our updated, improved geometry than we are here with our original 100 meter spacing. Okay, so you can imagine from this point on, combining Excel with your HEC-RAS simulation results, we could do various auxiliary calculations or show data in any way that you would like. Here's just, again, these are 2 examples. We could add, similar to how we add the water surface here, we could add the flow depth from the previous plot. That might be something maybe after this tutorial is done, you might try that to make sure you can do that to compare them. And we have now got our refined solution. So let's go ahead and save everything. And again, we should save our project often, and we're good to go. So in this tutorial, we refined our geometry using some of those tools that made things go really fast for us, like cross-section interpolation and copying cross-sections and adjusting the elevations. Then we imported our results into Excel, where we were quickly able to create plots and compare output from 2 different simulations. And you can see that beyond this, it's pretty infinite what you could do. So that takes us through the basics. The next tutorial is going to be sort of touch on a couple of topics that are not incorporated in this particular example problem from the text, but are things that as we go through them, you'll see that you could realistically be doing those for other problems, including changing the geometry, adding flow rates, and further data analysis. Okay, so that's it for this one.